In this example, we have empirically collected acceleration data at specified time, but unlike the previous example, we don't know what that underlying function was that generated it. So we can't compare it to a known value. So what we can do is come up with our best estimate as to if this is the acceleration, we want to estimate what is the velocity after about 12 seconds. In this case, we know what the initial velocity was, so when we started our timer, the initial velocity was 3.1 meters per second. So in this case, we have this empirical data that we want to enter into Matlab to start. So our independent variable t, we measured at 0 seconds, 0.97. And we enter the rest of this data. Right, so we have those 13 values stored in MATLAB here for our time and our acceleration. So what we want to do is look at the velocity now, or our estimate of the velocity over the same time period. So let me first plot our time versus acceleration. And dress this up a bit. This is our time in seconds. And our acceleration as measured in meters per second squared. Alright, so again, this came from our raw data here. And I made a typo. That's better. So the velocity is going to be the area under the acceleration curve plus whatever our initial velocity was, which was 3.1. So we see here that for the first about 9 seconds, 8.5 seconds or so, our acceleration is positive, which means our velocity should be getting larger. But then it drops below 0 for this, which means that after that point, our velocity should start to be decreasing. Since the area under A is, again, positive here, positive increase in velocity. Here it's negative, a decrease in velocity. So the first thing we can do is start with just traps, my independent variable t, dependent variable a. And by running this, this finds the area under the entire thing at once. So I found that the area was 74.82, but again we have an initial velocity of 3.1, so if we only want to know what's our velocity at the end, so at 11.88 seconds, what's our estimate of velocity? Well, we're estimating that the jet is traveling at 77.92 meters per second. But we're probably more interested in what's the profile of the velocity over this about 12 seconds. So in that case, I don't want to just use traps, which is just going to integrate from 0 to from my start point to my end point. I want to know what's happening all the way in between. So if I use cum traps here, now I have those velocity estimates at all of those points in time in which I sampled. So here I can plot this now, and this will be my velocity. I'm going to save this as large V. So again, I need that integration component, plus I have to add the initial velocity that I had. So if I open up this figure, now I'm seeing my estimated velocity at all those points in time. Now, since I'm using the trapezoid method, I'm making that assumption that all the points that I sampled were connected with that straight line between them. So this is my velocity over time. So we see that we're starting at near 0. It's actually not scaled quite. Let me get rid of this tight axis here. All right, so we see that we're starting at 3.1 at 0 seconds because that's our initial velocity. Our velocity is increasing, increasing, increasing. We get to this peak value around here at about, let's say, 8.5 seconds. And then we see that our velocity decreases. And this makes sense since when we looked at that acceleration graph, this point, the maximum on our velocity, was the 0 on our acceleration. So if we think of the relationship between a function and its derivative and a function and its integral, we know that a function has a max or a min when its derivative is 0. Well, velocity is maximum here because its derivative, acceleration, was 0 at that point. So what we might be interested in is, at least roughly, we can come up with what was the maximum velocity we saw over that time period. Well, according to these estimates, about 82.3 meters per second was the maximum. However, the last point in v, so that was at 12 seconds about what was our velocity, we dropped down to just about 78 meters per second since we have that deceleration around 8.5 seconds.